So this is problem 7.83. It's on page 405. As usual, draw the shear and bending moment diagrams for beam AB. Determine the magnitude and location of the maximum absolute value of the bending moment. So this beam is a little bit different than the ones we've seen so far. There's a distributed load along the entire length of the beam from A to B. The magnitude of that distributed load is 300 pounds per foot. First glance, this doesn't look all that different. There's a reaction at A and a reaction at B. What's interesting about this is there's an arm that comes off of this beam, something like this, that has a load of 300 pounds, and that load is 4 foot over from the end. The arm itself measures further 2 foot, and then there's 2 more feet to get to the end of the beam. So we'd like to come up with shear and bending moment diagrams and then figure out the how big is the maximum bending moment. What do you think we should start with? What we always start with, free body diagram. The free body diagram is going to be pretty trivial. I know that your intuition may be thrown off by this little curve, but it doesn't really matter what that shape is. The load is applied here at the center of the beam. So figuring out the magnitude of the reactions at A and B, well, first of all, they're going to be the same. Second of all, we can figure them out easily because 300 pounds per foot times 8 foot is what, 2,400 pounds, if I'm thinking right? Is 3/8 or 24? 300 more pounds means that the total load is 2,700 pounds. Half of that's going to be over here and half of it's going to be supported at the other side. So 2,700 pounds cut in half would be what, 1,350? So that's the overall free body diagram part. Okay. All right, so now for the shear and moment diagrams. Well, the shear diagram is not too difficult because all we've got to do is look at the load. You know what, let me ask you a question. Eventually we'll have to make a moment diagram in foot-pounds. This little arm's got to do something. What's that little arm going to do? It's going to make a moment, isn't it? Does that affect the shear diagram? No. The effect of that moment is already taken into account by the reactions, which seems kind of strange, but it is. So this is going to create a moment, and that'll make a step change in our moment diagram, nothing in the shear diagram, because shear is simply the integral of load. So all we have to do is begin at a load of 1,350, move down 300 pounds per foot. So if we move over 1 foot, we're down at 1,150. Move down 300, move over another foot, we're down by 600 pounds, whatever that is. What, 9, no, not 9, 8, I can't think. Doesn't matter. I think what I'm going to do is go all the way to here. So I know I've got 4 foot times 300 pounds. That's 1,200 pounds of change in the shear. Does that make sense? If the shear changes by 1,200 pounds going down, well then we must be at 150. I know that scale's not very good. Let's try that. We must be at 150 pounds of shear within the beam, right? But now we've got a 300 pound load which changes the shear by 300. So now we're at negative 150, just to the right of that central point. The load causes a continual decrease of 300 pounds per foot. So for 4 more feet, we'll move down at 300 pounds per foot. So we move down to negative 1,350 because 4 times 300 is still 1,200. 1,200 away from 150 is negative 1,350. And come back up to 0, okay, with the reaction here at the end. Any questions about that? Where should the moment begin? Well, at 0. There's no external moment, is there? As a matter of fact, I'm going to cheat just a little bit, since I can tell what's coming. I'm going to move this down just a little bit to give myself some more space. There won't be any negative moments to consider. So the moment begins at 0. How high does it go? Well, that's the same question as what's the change in the moment? Change is just equal to that area. What's that area equal to? Change in the moment. Well, we could calculate it. How would you calculate this area in a very easy way? Any ideas?
Split it into 2 sections.
I would not split it into 2 sections. That's difficult. Imagine doing this. Imagine, so you were thinking of splitting it into a rectangle and a triangle. Think about it this way. Let's just think about the triangle. If you were to cut off this top of the triangle and turn it upside down, it would fit over there, wouldn't it? So, what is this? It's the average height. So this height is simply 1350 plus 150 divided by 2. What is that? Well, that's 1500 divided by 2. That's 750. So basically all I've got to do is calculate the magnitude or the area of a rectangle that has height of 750, length of 4 foot. See? So take 750 times 4. We can do that in our heads because it's 2 times 750 is 1500 times 2 is 3000. Go ahead.
Wait. Quantity of 1350 plus 150 and quantity divided by 2 rather than 1350 divided by 2
It's
plus
the same.
150?
That's the same thing. Either way,
It's the same
pick your
thing?
pick.
Oh. Okay. Oh. Okay.
I'm just finding an average height, so technically it's the sum then divided by 2. Any questions about how I got 3000 for the change in the moment?
Hmm.
Did you go over it again?
I started
Sure.
listening to the side conversations. Listening to that. I mean, I get the where you come up with the 750, but then
So do you understand what 750 represents? How it's the average of these two heights? And therefore, this entire area fits perfectly right in there.
yes,
And that makes a overall rectangle whose area is easy to compute.
I got 2 different answers
What did
based
you do?
on. So for doing it, what you wrote up on the board, I got the 750. But moving the 150 outside, I got 825.
This is the same thing. Those have to be the same thing.
No,
Oh, why are we dividing 150 by 2?
because it's the sum of both.
Because it's
You're
the
just
sum.
splitting it across the 2.
We're taking the, we're
What
finding
Wilson
the
was
average
thinking
height.
about was if you just took the, divided the 1750 by 2. That's obviously going to be different. Because,
You mean the 1350 by 2?
13, sorry,
Sorry.
yeah.
Yeah, you wouldn't just divide that by 2. What I'm
Wait,
saying is
no,
find
okay.
the average height. That's why you have to add the 1350 and the 150. If what you're trying to do
Oh,
is,
okay. Yeah, no,
let's prove that this works, because this is a common trick that we'll use in other contexts. Let's do it the other way. Somebody had suggested calculating the area of a triangle. Okay, what is the area of the triangle? What's the height? 1350 less 150, that's the height of the triangle from here to here. Forget the 750, right? If you take that and multiply it by 4, the base length of the triangle, divided by 2, that gives you the length of the triangle, but then you have to add onto that the area of this lower rectangle. Well, that rectangle is 150 times 4, right?
what I had in my head it was that, but just the 4 moved to the
Okay.
outside-ist quantity.
I see. You should get the same thing with this. You should get 3000. Okay? Good questions. Anything else? I don't want to leave anybody behind. Okay, so the change in the moment is 3000. That means we need to go from 0 up to 3K, or 3000 foot-pounds. How will we approach it?
this would be an arc as well.
Arc, okay. Like that, or like that? Concave down or concave up?
What was the first one?
I don't remember which one I drew first.
Oh, the one on the left.
Concave down?
Yeah.
How many people vote for concave down? How many people vote for concave up? So about more than half the class is not sure. Look, we're adding a whole lot of area at the beginning. You move over a little bit, you add a lot of area. Whereas over here, you move over the same amount and you'll add less area. So remember, this is the change. This represents change in moment. The moment changes very little from moving in the horizontal direction here because we don't add much area. But over here, the moment changes quite a bit for a small move in position. So the correct answer is concave down like that. Okay. Now, what about what happens as we continue along? In fact, I think that I'm going to have to be more careful here, because I feel like that the moment that this is causing is going to cause a problem in my moment diagram. What I expect is to get a step change in the moment here, but in looking at this area is exactly the same as that area. So let's see. Let me do some checking. Let's try this. Let's make a free body diagram without that little arm. So just before we reach that arm. So at 6 foot, you can always go back to the free body diagram and check and make sure that everything is working out. 1,350 pounds, 300 pounds per foot. Don't need this anymore. How much shear and moment do we need?
You still have the 300 pounds down?
No, no I don't,
Yes.
because
that's
I'm taking a free body diagram from here back.
Okay, I was thinking it fell within that 6 foot span.
Well, I'm assuming this is right at 6 feet. I'm technically taking my cut just before 6 feet.
Okay.
Okay. So let's figure out the shear and moment required and make sure that the moment and shear I've got so far. Well, I haven't even reached 6 feet, have I?
No.
But let's just find out what happens. So we've got 300 pounds per foot times 6 feet. That's 1,800 pounds. So the resultant 1,800 pounds would act over at 3 foot. So if we were to look at the shear, 1,800 down, 1,350 up, let's see, we would need shear acting in the negative direction in amount of what, 450? So what I'm claiming is that right here, this is negative 450. Let's see if that makes sense. You know that the slope is 300 pounds per foot. How far have we moved over? By 2 foot. So we've gone down well, wait a second. 300 pounds per foot. We were right here at negative 150. So we've gone down, well, that says we've gone down by 600. Am I not thinking right? What am I missing?
From 150 to negative 150?
From 150 to negative 450 is negative 300, but that's only 1 foot worth. And what I'm doing over here is, did I do the math wrong? Let's find out. So V would be the difference between 1,350 minus 1,800, and that difference is negative 450. So I think I've got something wrong in my shear diagram because these two disagree. So what have I done wrong? I may have to back up and use free body diagrams along the length and just see what happens. So let's try that.
Where did the 150 come from?
What 150? Where? This?
Yes.
That comes from the fact we've got a change of 300 pounds. So let's see. Let me back up just a little bit. Let's move back, and I don't want to go on along the entire length of the beam, but maybe every 2 foot or so. Let's see what happens. So 1,350 shear moment distributed load. Okay, so for 2 foot worth of beam, let's see. Yeah, for 2 foot worth of beam, I'd have 300 pounds per foot. So that's a resultant of 600 pounds acting over at 1 foot. So now what would the shear have to be equal to? Well, let's just sum forces. So 1350 minus 600 minus V has to be equal to 0. So V is equal to 1350 less 600. So that's what, 750? So the shear should be equal to 750 when we're at 2 foot. Let's check and see if that's true. So at 2 foot, X in feet by the way, we must come down 300 pounds per foot. So 1350 less 300 would be 1050. Less 300 more, 1050, what? 987, 750. So that works. So far I like it. From here to here, things seem to be okay. Let's go to 4 feet or just before 4 feet. You know what I bet? I didn't include that 300 pounds, but I shouldn't have to. I'm taking a free body diagram. Yeah, it shouldn't include that. All right, so let's go over to 4 foot and see what happens. Because I think I'm missing something. I'll pick it up. Okay, so the resultant.
Well, if you would have included the 300 in the previous.
Yeah, but I can't. The free body diagram doesn't include that part.
Okay.
All right, so the force downward 300 times 4 is 1,200 pounds. I should put that in a different color to show it as a resultant. 1,200 pounds, which acts over at 2 foot. Now looking at the shear in a moment. So we got, let's see, 1350 minus 1,200 minus the shear equals 0. So the shear should be equal to 1350 less 1,200. Sure enough, that's 150. So far so good. I know what's wrong.
Is the force not applied to shear at where
I think that's
the
what's
force
wrong.
is, but where
Yeah.
the member is?
I think so. It's over here, right? So the force from this little segment is applied right here, not here, because this is not part of the beam. So what this will do is it'll apply a force and a moment. So when I moved over, I should not have done this. I should continue to go down, because as I take free body diagrams moving farther and farther, I should not include that, and I did, and that was actually a mistake. Okay, so the shear would actually continue downward.
The weather keeps changing every 5 minutes.
So does my problem solution, apparently. Alright, so for 2 foot, let's see, we're going to lose 600 more pounds. Yeah, that'll work. So actually, the slope doesn't seem to be right. So what do we have? It would be 6 times 300, so 1,800. So I need to move down by 1,800. So 1,800, that would put me at negative 450, which is where I expected to be. So that makes more sense. So negative 450. That makes more sense. And at this point, we're going to have a force of 300 pounds applied. That'll move us down to negative 750. And then, if we add up another 600 on top of that, yes, that brings us down to 1350. Okay. All right, so I had a mistake in my shear diagram. So, that means this moment's going to come out to a higher level than what we had. In fact, it would be maximum right there wherever it crosses, and we've got to figure out where the line crosses. Okay, the free body diagrams helped me. Good. So where does that cross? Well, basically, it's going to cross wherever 1350 minus 300 times x equals 0. We've got 1,300 pounds. We have to erase 300 pounds every foot. We move over 2 foot, we've erased 600 of those pounds. Move over 4 feet, we've erased 1,200 of those pounds. But we still have 150 pounds to erase because 4 foot is right there, okay? So if we rearrange this 1350 divided by 300, by the way, let me put the units in here and it'll make more sense. That's 1350 pounds minus 300 pounds per foot times x feet equals 0, okay? So x in feet would be equal to 1350 pounds divided by 300 pounds per foot. So take your calculators, take 1350 divided by 300, what do you get? 4 point something, I don't know what. 4.5. 4.5, thank you. So where that crosses is at 4.5 feet. So we actually have to go all the way to 4.5 feet in order to find the moment. In other words, we want the area of this entire triangle. And that whole discussion we had earlier about triangles and rectangles becomes useless, doesn't it? So 1350 is the height of the triangle. The base length of the triangle is 4.5. Since it's a triangle, take that rectangular area divided by 2. You got the area of the triangle. So take 1350 times 4.5 over 2. What do you get?
Is it 4.5 divided by 2?
1350 times 4.5 over 2. Yes.
It's 3,037.5.
3,037.5?
Yeah, just like that.
Okay. It's still concave down, like we said before. Okay? Now we need to calculate the amount of negative area up to the point where this little segment is attached that's causing us so much trouble. So that area is negative 450 times the length. Well, the length is from 4.5 over to 6 feet. So that's, despite my drawing, that's 1.5 foot. And then divide by 2. Everybody see what I'm doing? I'm just calculating the size of this triangle, the area of the triangle. We're at 4.5 feet here and 6 feet over there. So that's a base of 1.5, which is where that came from, and a height of negative 450. Okay? And that's the wrong area. It would actually be this area. They're the same, but that's technically more correct. So what does this result? 450 times 1.5 over 2 is what?
Negative.
It's negative 337.5.
Yep, that's what I got.
Negative 337.5. So if we move down by 337.5, well, the 37.5 is gone, move down by 300, we're at 2,700. So our moment goes down to 2,700 foot-pounds. Now, we can't just add up the rest of this area, because if you think about a free body diagram just past 6 foot, well, then we're going to have that little arm on there with the 300-pound load, right? Now let's consider what happens to the moment when we include that 300-pound load. So we've got a shear of, looks like it's negative 450, so it's actually up like this. But what is the moment equal to? Sorry, this is squished together. Well, we've got a reaction back here of 1350. A distributed load over the 6 foot span of 300 pounds per foot. Don't need that anymore. Don't need that either for that matter. Okay. And so now if we sum moments, counterclockwise positive. Have I missed anything? I don't think so. I think we've got it all. Well, we've got some moments about this point, so about x equals 0. Let's see, we're going to have a resultant of the distributed load over 6 foot equal to 1,800 pounds. 3 6s are 18, so that works. And the shear will also cause a moment, so let's just put all this together. So we're going to have negative 1,800 pounds times 3 foot. Okay, so that's the moment of the resultant. Then we're going to have plus 450 pounds for the shear times 6 foot. What's that? Let's not forget there's a moment in the beam as well that is causing a positive moment. And then there's this 300 pound load causing a negative moment. So minus 300 pounds times, well, that's a 4 foot moment arm. So now all we have to do, let's see, that's the distributed load as a resultant, the shear, and the external load, so we're set. All we have to do is solve for the moment within the beam, M. So move everything to the other side. 3 18s are what? 36, 18, 46, 54? Thinking right? Yeah, we'll just leave it this way. 1,800 times 3. Moving this to the other side, minus 6 times 450. Moving this to the other side, plus, well, 300 times 4, I can do that for you, 1,200. Okay? So what's the magnitude of the moment just to the right? And I'll show you another way we could have gotten this. So 1,800 times 3, that's what, 600, yeah, 5,400. We need to subtract off 6 450s. So 6 500s is 3,000. So subtract off 3,000, 3,600. Add back in 6 50s. Add back in 300. Is it 3,900 at the moment? Okay. Notice what I'm doing here. I'm calculating the magnitude of the moment itself, not the change in the moment. I know the moment had better be. No, wait a second. I put one of these in the wrong direction.
Is
Oh.
it because of the jump?
I
because you
used-
suddenly gain.
I used the wrong shear. Remember I said I wanted to go past this point and I used 450. I should have used negative 750 rather than negative 450. So that should be 750. Let's try that again. So this is 750. There we go. So try again. We still have 6,600 from these two, but we need to subtract 6 times 750. I'll let you guys do it. What's the result?
I got 2,100.
2,100. Okay. So the moment just to the right of this is at 2,100. How could we have come up with that magnitude directly? We could have considered this 300-pound load to cause a concentrated moment at this section. Basically, the 300-pound load times its 2-foot moment arm gives us a 600 foot-pound moment, and notice the movement down was by 600 foot-pounds. See that? So had we thought about it that way, as this causing a concentrated moment at this point, we could have simply calculated and drawn it, rather than taking the whole free body diagram. Okay. Another way to look at this is to replace this segment with a load here. Think about it this way. If we have that little arm, let's pull it off the beam, with a 300-pound load here, well, something's got to pull up here at 300 pounds, doesn't it? To keep it in equilibrium. Not only that, but there also must be a moment, because see, we're trying to do this, so there must be a moment acting on it of what? Well, let's see, summing moments about this point, 4 foot times 300, not 4 foot, 2 foot times 300, of 600 foot-pounds. Notice these are forces and moments acting on this little segment. Therefore, if we completely eliminate this segment, which we can do safely, we could say there's a 300-pound load at this point and a moment of, let's see, we gotta go the other way, so like this, a moment of 600 foot-pounds. And had we used these, it would be a lot simpler to see that, and I wouldn't have messed up, because then when we move over, we don't encounter a load of 300 pounds until we get to 6 feet. We also don't encounter this moment of 600 foot-pounds until we get to 6 feet. Does that make sense? That might have been a more sensible way to approach it. Okay? Any questions about what all we're doing so far? Last thing is to figure out if all this makes sense by calculating this area. We should end up back at 0. So I hope that this area, the change in moment, is a negative 2,100 foot-pounds. That's what I hope, but let's find out. How could we do it? Well, use what I showed you before. Take 750, add it to 1350, and what do you get? Well, it looks like you get
2,200.
2,200? 2,100, right?
Wow.
But then I think we've got a problem because then we've got to multiply that by 2 feet, don't we, to get the area? I feel like there's still a mistake here somewhere. Did I do the math wrong? 100, no, I don't think so. Are my reactions wrong? Let's consider that. That's possible. Possible that my reactions are wrong. Now that I'm thinking about it this way, I don't think they're wrong though. I think my reactions are okay.
Should they be different because it's closer to B rather than center?
But see, if I take an overall free body diagram, it shouldn't make any difference. But let's check. Let's try this free body diagram and see if we get the same 1350 reactions. All right, so the resultant there is what? What's the length of this beam? 8 foot, right? So 2,400 pounds. Because 8 times 300 is 2,400. No, it's not. It's 3,200. No, what is it? 3 8. 8 and 8, 16 and 8. No, it's 24. 2,400. You guys okay? You're not correcting me at all. Are you behind in the dust, or are you okay? You up with me or not? All I'm doing is trying to calculate the resultant of the 300-pound load. For every foot, I got 300 pounds, right? But I got 8 foot. So I just need 8 times 300. So I think it's 2,400, right? Okay, all right. So with that, I should be able to say some moments about point A, counterclockwise positive. And then I'd get what? Negative 2,400 multiplied by 4 foot. That's the moment of the resultant. And then minus 300 multiplied by 6 foot. There's a concentrated moment of 600 that's positive, so plus 600. Okay. And then we'll have the moment of point B, so plus B times 8 equals 0. Okay, so let's see what B is equal to then. So B is 4 times 2,400, moving this to the other side, plus 6 times 300, moving this to the other side, minus 600, all divided by 8. Okay, so grab your calculators. 4 times 2,400 plus 6 times 300, minus 600, and then divide the result by 8. What do we get?
1350.
1350. So my reactions are okay. They're correct. So what am I doing wrong here? We only need, what, 650 to get to 2,000? So, oh, I forgot to divide by 2. That's what's wrong. I was trying to calculate an average height, and I just took 750 and added 1350, then started panicking. Mm-hmm. The area is, okay, so the average height here is not 750 plus 1350, it's that sum divided by 2. Yeah, so then when we then multiply by the 2, whoop, the 2 foot length, we'll be okay. So yeah, so the area does come out to 2,100. We'll get it in a second, thank you. It does come out to 2,100. Now, should I make this concave down, concave up, straight line? What do you think? It's concave down, right? Because we add more area at the beginning. There's more change per per length, per movement. There we go. All right. We made it. Any questions about this problem? Yeah, what was that part from the beginning to the end? Repeat that?
I like think I actually understood it. Like,
You understood?
Yeah.
Okay.
Especially the first two problems. This one got tricky for a little
You
bit.
got a little
lost
tricky.
a little in there,
Yeah.
but the first two I think I got.
Okay. Anything else? All right.